Okay, so welcome to my session, What the CRaC? Coordinated restore at checkpoint on the Java virtual machine. So let me try to get you hooked on CRaC, but only for your JVM. First about me, my name is Gerrit Grunwald. I'm working for Azul Systems as a developer advocate, and I love GeeCON. Yes, it's an awesome conference. Woo! All right, Java is great, right? We know that. We have a vibrant community. We see that with conferences like this, community-driven. I love it, so it's awesome. And we have hundreds of jugs, which is pretty cool. And we have thousands of free open source software libraries. And I think that makes Java, the Java ecosystem quite unique. But the real star of the whole Java ecosystem is the Java virtual machine. And the question is, how does it work, right? So let me give you a short, very simple overview on how it works. So you have your source code. It's a Java file. You compile it, Java C, you get some class file out of it that contains bytecode. So then we take the bytecode, put it in the class loader loads it into JVM memory. From there, from the JVM memory, it goes into the so-called execution engine. This is just a very simplified version of the execution engine. It contains more than that. But we will just focus on these three parts. There's the interpreter, there's the C1 JIT compiler, former known as the client compiler, and there's the C2 JIT compiler, which is former known as the server compiler. So how does it work? So first of all, the interpreter takes the bytecode from the class file and compiles it into instruction set code of the CPU, of the current architecture. And the hotspot, or the JVM, is just counting method calls during this run of the code, and it detects so-called hotspots, which is the reason for the name of the hotspot compiler, right? The hotspot JVM. And then it takes these hotspot methods, pass it to the C1 compiler, and the C1 compiler then compiles the code as quickly as possible without a lot of optimizations. Here the goal is really create compiled code as fast as possible. All right. Once it's compiled in the C1, the JVM profiles this running code and figures out so-called, or let's say like hot code, right? So code that is executed over and over again. So and then it takes this hot code and puts it into the C2 compiler. The C2 compiler is slower than the C1, but has very high optimization, so the best possible. So this is in principle how it works, and that is great. But the problem with this is it takes some time, right? As we all know. So that means if we take a look at the JVM performance graph, then we see the little yellow on the lower left corner. That's, for example, the interpretation phase. And then we see the green part, which is more or less the profiling of the C1 code. And then we see the blue stuff, which is the C2 stuff. So, and we see at some point we reach some threshold where the application runs at its optimized speed. And usually this time is what we call the JVM or application warm-up time. And that really depends on your application. It could be seconds, it could be minutes, it could be hours, it could be days, I heard. So it really depends. And then you see this little gaps in between, and that's the so-called de-optimizations. So that means if you have a JIT compiler, it makes a lot of speculative optimizations. That means method inlining, branch prediction, and stuff like that. And if it was wrong in predicting something, then at some point it has to de-optimize, and that means it goes back to the interpreter, back to C1, back to C2. So this is something we would like to avoid, but it happens. That's JIT. If we now take a look at a microservice environment, then that means we have our application running, first instance, start, warm up, second time we run it, warm up, third time, warm up. You see where that leads to, right? So this is not very satisfying in the end. So wouldn't it be great if we could do something like that? Start it up once, warm up once, and then run at full speed. Second run, full speed, third run. From there on, always full speed. That would be great. Well, then the question is, what about app CDS or CDS? Did someone attend the session before this? I think it was at 10. That was all about CDS, and it's nice. It's class data sharing. You can have app or dynamic stuff. It dumps the internal class representation into a file and then loads it from the file, which is optimized and much faster than going through the standard process. And it's shared on each JVM start, right? Now that's cool. The problem is you don't have really optimizations there because this is only loading, and there's also no hotspot detection in this case. That means it reduces the load time of classes in the end. And that could get you 1 to 2 seconds. That sounds a lot, but you know, if you have a big Spring Boot application, for example, startup time could be in the range of 5 seconds. So that means still 3 seconds, right? It's okay, but not really maybe the thing that we would like to see. What about ahead of time compilation? So ahead of time compilation in principle is always static compilation, means you compile the stuff once, you don't interpret, no analysis of hotspots, no runtime compilation of code. It starts at full speed straight away, right? Awesome. GraalVM native image does exactly that. So I'm done, right? Can go, we know, GraalVM, but wait. Not as fast, because AOT is by definition static, right? That means the code is compiled before it is run. Compiler has no knowledge of how the code will actually run. That's a big difference, right? You saw the warm-up phase that we have. There's a reason for that. And this is application warm-up phase. And then there's this so-called profile-guided optimization, or PGO. This is a way where you can add a profile to the native image and make it faster, but even that doesn't really give you the same performance. So let's compare AOT versus JIT just shortly. If we have AOT, we can't use method inlining, where the JIT can use aggressively method inlining, right? So method inlining, just in short, is something, if you have a class, you have a property in that class, and this property has a getter. And when you access it, you usually call the getter. Method inlining would mean you can directly access the variable. So you really get rid of this calling the method. And stuff like that could make the whole code much faster. There's no runtime bytecode generation in Graal or in native image or AOT in principle. You can use runtime bytecode generation in the JVM, of course. That's not possible. That's all possible. Reflection in Graal is possible, kind of, quite complicated. In JIT, reflection is it's never simple, but it's of course possible, and we use that a lot. You can't use speculative optimizations in AOT, where you can use that in the JIT. That means, for example, stuff like branch prediction, where the JVM decides during the profiling phase, it sees, okay, this method has, for example, an if-then clause, and the if clause is called very often. So I optimize the code only for this part and get rid of the else. And later on, when somehow this else clause is called, then we have this de-optimization. That means the whole stuff has to go again through interpretation, C1, C2, and but this is possible using JIT. This is not possible using AOT. That means the overall performance of the AOT is typically a bit slower than the overall performance of the JIT. Well, on the other side, with AOT, we have really fast startup time. The JIT needs warm-up, as we saw, and there's no CPU overhead when you compile the code at runtime, where we have that in the JIT. Because AOT, you do the whole compilation up front, it's done. You start it, it's working. So, again, the JVM performance graph. This is the JIT. Now let's see if we do AOT. That will bring us here, roughly. And even if we use PGO, will bring us a little bit more, but we don't really receive the whole 100% that we can get from a JIT. Right? So you can get close to it, but you can't really, because the JIT, you have to think about the JIT can always, during runtime, optimize the code. And it can react on the behavior of the application and the JVM. which is not possible in AOT. This is, you did it once, you run it, and that's it, right? There's no way to optimize. The JIT can. So let's take a look at a different approach. There's this project called CRaC, which is checkpoint restore in user space. And this is a project, this is a Linux project. It's part of kernel since 3.11, so it's quite some time in the kernel. And it was made to freeze a running application or container. That was the idea behind it. And what it does, it creates a checkpoint or a snapshot of this application or container and stores it to the disk, right? At runtime. And then you can restore from this snapshot the whole application or the container back again into memory, running. And this is already used. It's used by OpenVZ, by Linux containers, by Docker, by Podman. They use this library or this project to make that happen. And it's mainly implemented in user space, right? So it's not in the kernel directly. The main goal was the migration of containers for microservices. As we all know, this is the future at the moment. It heavily relies on the /proc file system, so this is the reason why it's only available for Linux at the moment. It can checkpoint or snapshot as you like, and it can do stuff like processes and threads, application memory, mapped memory files, shared memory, open files, FIFOs, sockets, inter-process communication channels, timers and signals, and it can also rebuild TCP connections from one side without really exchange packets, right? That's a quite impressive project. And the challenges are, so if you would like to restart from a saved state on another machine, you can imagine that's not easy, right? You create the checkpoint on this machine, take the stored file, go to another machine and open it there, because you don't know if you have the open files there, if you have the shared memory and all that stuff. So that's a challenge. Start multiple instances of the same state on the same machine. Also not so easy, because as we know on Linux we have PIDs for each process, and this is stored, and if you restore the PID, and you can't really restore 2 times the same PID on one machine. There are ways to do that, but usually this is problematic. And a Java virtual machine would assume it was continuing its task. So that's very difficult to execute here, to use it effectively. So that means just CRaC alone doesn't work here. But there is this new project called CRaC, which is a coordinated restore at checkpoint. That means instead of just doing it on a more operating system level, we just have to somehow find a way to make it possible, implement it within the JVM. So CRaC comes bundled with the JDK, that's the idea. And the heap is cleaned and compacted, so we make sure that the JVM is in a safe state. It can throw exceptions in case, you have a file open, or there's a socket open, or still a database connection, so it lets you know if something's wrong. It comes with a very simple API, and it can create checkpoints using code, or you can use JCommand to do that. The whole thing is available at OpenJDK project/CRaC, and it's led by one of our engineers, Anton Kozlov. And if you would like to know more, you can just check that website, and then you will see what it is. Just give me some more information about it. So what it does is, it has more restrictions than CRaC, right? So for example, you can't really handle open files and just save them and restore them. Also not sockets, database connections, stuff like that. So it's needed that if you stop the running application, you have to the application needs to know, I will be checkpointed, right? And once you restart it or restore it from that checkpoint, you also have to let the application know, now you will be restored from a checkpoint. So you need to be aware of that. So there is the way to start it is, for example, Java -XX:, and then there's this CRaC checkpoint 2 equals, and then you can get it a path. That means once you start the jar, you just pass the parameter where it should store the checkpoint. And if you would like to restore it, you just call Java -XX:, and then CRaC restore from the same path. That also means you could create different checkpoints and restore from different checkpoints. That's possible. For example, we had it at a other conference where someone asked, okay, we have one program and it runs for different sorts of applications. So that means one department uses it in that way, the other one in this way, and the third one in that way. Can we create different checkpoints for all of them? Yes, you can. And then each one can restart from the same checkpoint. So I told you there's a simple API, and it's really simple. It's just one interface. It just has two methods, before checkpoint and after restore, and it's called resource. And what it does is you have to add your class where you, for example, you have a database manager that connects to MongoDB or whatever. That database manager has to implement the class, and then you get two methods, the before checkpoint and after restore, and then in these methods you can react on the creation of the checkpoint and also on the restoring of the checkpoint. And so that means you get you receive callbacks from a so-called core context. I will tell you in a minute what that is. So, and that makes it possible that you can really react on the checkpointing itself. So it's up to you to say, okay, this class will now be checkpointed. I have to save these files. I have to close these connections, whatever sockets. And when you get to restore in the after restore method, you can do it vice versa. You can just restore the internet sockets. You can load the files that you need, whatever you need. So that means the resource objects need to be registered with a context so that they can receive notifications. So it means there's one specific class that takes care about calling all these resources and also when they get restored to call them. So this is called the context, and you can get it by core.getGlobalContext. I will show you some code later on. So this is in principle how it works. You have your class, you implement the interface that gives you the before checkpoint, after restore, and then you register this class to the context. Right? So that's it's pretty simple. Right? So in the global context maintains then a list of all the resources, of all the resource objects in your code. And it makes sure that the before methods are called in the order you restore it. So, you register it. That means you take care that, for example, first the database manager gets registered as a resource. Then the second one will be whatever manager or database or internet connection or open files. And then when you restore it, the context will make sure that they will be called in the reverse order to make sure that you get to the same state as you left the application. So you can do that by checkpoint restore method in the core. By programmatically, you can just add it to your code. That means you can run the code, and then at some point you can decide, okay, now the JVM is warmed up, everything's fine, I create the checkpoint. Or you can use J command and do it from the external side, just from the command line. Because what you usually do, you have to think about like this. You create your application, you start it, you warm it up, you create the checkpoint once, and that will shut down the JVM. And then after that, you can use these files and just restart. So that means you can do it programmatically, but in principle, it's totally okay to use J command to do that. So let me give you a simple example. I created some code. That is, it's a scheduled thread, and it will be called every 5 seconds. And what it does is, it goes through a loop. This loop runs 100,000 times and checks 100,000 numbers if they are prime or not. And this is a random number. So that means it calls the method isPrime, then it checks is the number in the cache. If it's in the cache, it's directly returns it from the cache and it's fast. If it's not in the cache, it has to check the number, is it prime? And the result will then first go to the cache and then it will return the result. So this is definitely slower, right? Because you have to do the calculation every time. And then to make it a little bit more realistic, every 60 seconds, the cache will forget the numbers, right? So each number will be stored with a timestamp. And if this is older than 60 seconds, it will be wiped out. That's the idea. So that means the first run will be pretty slow because every number has to be calculated because the cache is empty, right? Then these checks should be faster and faster, because the more the cache is filled, the faster will be the results back, and so on and so on. So with each run, we should see a decrease in this time. So I made some measurements on one machine, and that was how it looks like. So after 8 iterations, roughly, I got to the point where it goes around 1, so the performance. So that gives you, in principle, it's the same like your application warm-up time. On this machine here, because I have to run it on a virtual machine, it's a little bit slower. It needs 15 iterations to do that. So the demo, and I go through the demo once now on slides, and then afterwards I will show it to you in reality, but I have to do some explanations. That's the reason why I show that in slides. So we have 2 shells that I have open. On the left one, I start the jar file, right? And here you see I define it should go in the folder /CRaC -files. And then when it starts, the first run will take around 27 seconds on this machine, right? And you see it's 63% of the cache is filled. Then the second run just only takes 10 seconds. Then it's just 3.8 seconds, 1.3, and it goes down and down. The more we have in the cache, the faster it will get, of course. So then when we reach this 14 milliseconds, for example, that means the cache is nearly completely filled. We can't get a lot faster than this. So in that case, we create the checkpoint from another shell, and I just call JCommand, I call the jar file, and just say jdk.checkpoint. And then it will create a checkpoint, and it will lead to this. You see, it will show me on the right side where I created the checkpoint. It will show me the PID, and you can see on the left side that I printed out so that we can see, okay, this is the PID of the process. We see before checkpoint is called in the main class and also in the generic cache, and then it creates the checkpoint and kill the JVM. So that's how it will work. And when I do, and this between the arrows, this is the application warm-up time. And then when we restore it, I just call again Java. I link it to this folder, CRaC files. And when I start it, you see it will continue counting from 8. The last one was 7. And you see that the time is directly fast because the cache is still filled. We checkpointed the complete JVM, including the cache. And the only thing we do now, we just load it from the file system back into memory and start it. And that's all. Nothing else. No compilation or something is going on. That's all done. It's directly running. And you see the cache is still at 99%, and it's 19 milliseconds, which is quite fast. And then it stays like that. So now I have to tell you that there was a little tweak needed to make that happen. And if you remember, I told you the cache will forget every 60 seconds the numbers it got. So it means when I create the checkpoint and I stop the JVM and I wait a minute or 2, what should happen? When I start it up, next time I ask the cache will check against the current timestamp, and it will tell you, oh, everything's outdated. And it will wipe out all numbers. And usually that would lead to the fact that after restoring, it will go through the same warm-up phase, right? That's the problem if you really do a checkpoint that is where you have data that is time-based or date-based. Yeah? Then you really have that problem that you have to take care about that. So what I did is when I create the checkpoint in that method before checkpoint, I just store the current timestamp in a variable, and that will be then also be in the checkpoint, right? It will be with the files, it will be stored. And the next time I start it up, I check if this variable is set, compare it to the current timestamp, and take the delta of it and add it to all values in the cache. And with this, I can make sure that it's on the same state. But this is stuff you have to do if you depend on time critical stuff in your code. So, like I said already, you can, from the command line, you can create the checkpoint like this. Or if you are in code, you can do it like this, core.checkpoint restore. And this demo that I showed you is also available on GitHub, so you can check it on your own. It's not really complex code. It's very easy. That was the reason why I created that as a just simple demo to show you what's possible. Okay, that's my demo code. But how good is it really? So our engineers made some tests. We took a Spring Boot application, a Micronaut application, Quarkus, and some XML transform stuff. And you see, that have been the times that we found that startup times. So time to first operation. You see Spring Boot was around 4 seconds, Micronaut 1 second, Quarkus below a second, which is quite fast, and the XML transform 4.3 seconds. So if we run that on the OpenJDK using CRaC and restore it from the checkpoint, then this have been the numbers. And I think that's quite impressive. This is in the range of native image of Graal. It could be even faster than that because we don't have to do anything. We just have to load it back into memory and start it. It's just there. We don't have to do any compilation or execution. And you see that the numbers are pretty much in the same range. The reason for this is, as you can imagine, I just told you, we just store the complete JVM into a file, the whole thing, right, the state. And then we restore it from there. So the only dependency we have is the speed of your file system. That means the faster you can load it, the faster it will restart. And that leads to the fact that we see very similar startup times here. Of course, if you have to do, for example, if you have to restore a lot of resources, then it can take a little bit longer. But this is always in the range of milliseconds. So we can really bring down, you saw in my demo stuff, and I will show it to you later on, you saw that I also was in the range of 14 milliseconds, 15 milliseconds, because I don't really have to restore a lot of resources. Where, for example, the Spring Boot application, Micronaut and Quarkus, they have to do some restoring of resources. Okay, then we have it here in another chart where you can see the red line is running the Spring Boot application on OpenJDK, and the blue one is OpenJDK on CRaC. And it's time to complete n operations. In this case, it was 100,000. And you see in the beginning, you see this warm-up phase, right? Before the OpenJDK is warmed up, the JVM, you see it's slower. Where the CRaC version, it's linear because everything has been done already. So we have an optimized code. It's so to say a hot JVM directly running at full speed. And the same for Quarkus. There, the overhead is a little bit bigger in this case, but again, we see this curve in the beginning, and in the CRaC stuff, we don't see it. It's just there. Okay. Summary. CRaC is a way to pause a JVM-based application. Doesn't matter what you run on that, right? Could be whatever. If it runs on the JVM, you can checkpoint it. And then you can restore from that checkpoint in the future without any problem. The benefit is it's potentially extremely fast time to full performance level because it's really just the loading time, nothing else. And it eliminates the need for hotspot identification, method compilation, recompilation, de-optimization and all that, because that was done in the first run. And of course, I have to agree, if you run it the first time, you have to warm it up, and that depends on your application. But once you did that, from that moment on, you can just go and always start it from that point. And that's huge. The benefit is really huge. And we have improved throughput from start, and it's an OpenJDK project. So if you go to github.com/CRaC, you can find all that stuff. Also the demos that we did with Spring Boot, Quarkus, the code is there. You can run it on your own if you don't believe me. It's everything is there, the whole project. You can also find it because an official OpenJDK project, you can go to wiki-openjdkjava.net/display/CRaC, and you will find it there. If you just search for JDK CRaC, you will also get to these pages. Okay, now we come to my little demo. Let me see. Okay. No. So on the left side, I just put the start things into a shell script. So it's not really magic. It's really just calling the Java -jar and then the -XX and so on with the folder. On the right side, this is the other shell where I just create the checkpoint. This is just calling the J command. Okay, let's start it. So we see the pit, and then it will take around 27 seconds, the first run, until the cache is really filled. This is because of the virtual machine that I'm running here. So if I run it on my M1 MacBook Pro, then it takes 1 second for the first run, and then it goes so fast that it doesn't really make sense to show you, because like done. So here it was, lucky me, it was a little bit slower, so you see really the impact. Because it's in the range of seconds, you see 28 seconds the first time, and then the second run will be 10 seconds, and then it goes down. We have to wait until the 15th run until it really settles, because there's some de-optimization at, I think, run number 12. You will see that. So we are down to 19 milliseconds, and now you will see it takes a little bit longer the next time. Or maybe, I think the 12th run was the slow one. And I know that because it's always the same. Okay. If we reach 15, it will be around 40 milliseconds, and this is the time it's settled. And then I will create the checkpoint. Okay, 50. Checkpoint. So, checkpoint created. And the problem here is it always says on the right side, command executed successfully, even if it throws some exception. I mean, it's still under development. So just if you try to run CRaC, and you can do that, because there is an OpenJDK version available in that on that openjdk.net page, and that's the one I use, and it's only available for Linux x64. So that means if you would like to run it on your own machine like I do here, you need either a virtual machine where you can run Linux x64 or you have a Linux box. So unfortunately on my M1 Mac doesn't work, but this is my old machine and it's a x64 Intel, so on this one I can do it. Okay, so we see it called in the main the checkpoint method and then in the cache, and if I restore it, you should see that it will first call the restore in generic cache and then in main. So it keeps the order, right? So it means in order when it's checkpointed, and when you restore it, it's the reversed order to make sure you can really, you have the control of shutting down resources and restoring them. Okay. So now let's do the restore. And just watch out, we are at run number 15. That means the next one should be 16. And it was 51 milliseconds, so if I'm right, it should be fast. Here we go. And there it is. 55 milliseconds, and then it takes 5 seconds between each run, right? But you see, we are down, and it's just fast. And that's the main effect. And you see, even if my demo code is very small, we are in the same range as we saw with the Spring Boot application. It really just depends on loading time from your file system. It's not really related to the code that you use, because that is already compiled and optimized. So I can stop it. And now I can just restore again because I saved the files, right? Okay. Go again. You see it starts from 16, 42 milliseconds. It always depends a little bit, but you can see the startup time is fast. Now the problem is, or let's say the goal is, it doesn't make sense to do it like this, right? The really useful thing would be to put that in a Docker container. You warm up your application, you have the checkpoint, and then you create a Docker image with this checkpoint. And then you can run that as often as you like, parallel if you like, and it will always start up like this because we just have startup times below 50 milliseconds. That's the main idea behind it. So let me also show you how large is the file set. Okay. So this is the files from my application, and it was around 30 megabytes. This is the biggest one is here. So that means, of course, if you have a huge application, these files will get big, but I think hard drive space is not really the problem here. So that shouldn't be a big deal. Even if it would be hundreds of megabytes, it's not really a big difference. We have also other demos now for AWS Lambda functions. I didn't have it in my slides, so you can find it on the GitHub repo that I showed you. And with this, I'm really fast. I'm surprised. We still have 15 minutes left. And if there are questions, I'm happy to answer them. Oh, therefore I need to my app. Sorry. Okay. Do you know if there are any Spring Boot integration efforts? You mean Spring Boot integrating with CRaC? If this was the question, then no. As far as I know, not at the moment. The problem with this CRaC project is that it is an official OpenJDK project, but I also mentioned it only runs on Linux at the moment, because there's nothing like CRIO, right, on Windows or Mac. I mean, this is not the preferred platforms. Windows and Mac is usually not the stuff that you run on your servers. This is Linux. And it will be available for ARM64, that's for sure. But it's not now, but it will come. So the idea is maybe creating something like a shadow interface that comes then for everything. That means you can code it on Windows and Mac, but it doesn't do anything. And if you deploy it to a Linux machine, it will work. So that's some of the ideas that we are thinking about. But at the moment, it's really, that's the reason why I'm here. I would like to hook you on CRaC, talk about it, play around with it, because it's really fun. Second question. When we deploy new versions of an app, can we restore the resources from previous versions? Yes, of course. Because this is, like I said, you really store the whole JVM. So you can restore that every time. As long as you use the same JDK, this is something that might be different. But if you create a new version of your app, no problem. Then you have a new version, right? You can't assume that this is then coming from the checkpoint, right? From the checkpoint, you get the old version. You can create as many checkpoints as you like, and you can start from them wherever you like. It doesn't matter. It just creates a set of files, and you tell which files to use to start it up. Would it be possible to incrementally update a checkpoint after a code change without rebuilding it from scratch? Oh, that would be great. I would love that. At the moment, not. So that was my idea. The first time I saw it, I was like, that's cool. I can do something like undo, right? Just store the stuff all the time and then jump back or just add stuff to the checkpoint. No, that's not possible. Checkpointing always does the complete thing. So you can't really incrementally do that. Is the snapshot somehow bound to content of class path? No, usually not. So like I said, you really have to think about, you take the JVM and just drop it in a black hole. And then at one point you just grab it out there. The JVM has no idea what's happening. This is the main idea, really, to make you independent from all of that. It restores the complete JVM with your application at that point when you created the checkpoint. Should JVM always be killed after taking a snapshot? Yes, it will do automatically. I would love to see something like just create a checkpoint and continue running. But you can imagine if you have to close resources and all that. So at the moment, it's not. I started that discussion internally that it would be great to do something like you run the application and at some point you can decide, create a checkpoint. And then maybe afterwards, at some point you say, oh, now I would like to go back to this specific checkpoint. But that's not possible at the moment. It might come, I don't know yet. How can this speed up my, sorry, it's jumping. How can that speed up my development cycle? Can I leverage it somehow to get faster feedback loop? Good question. How can it speed up your development cycle? So if I see development cycle means you're just developing all the time, right? So it means you change the code. Then that would also mean you have to recreate the checkpoint all the time. I mean, it's fast creating the checkpoint. Not sure if it really gives you some benefit there. So it could be, but I will be honest, I never thought about that. So I have to think about that. Can you share the GitHub link again? Of course. Wait. Where is my... Why don't I see my... Wait, just give me a second. I just have to restart this one. And the link This is the demo. I have to jump through the... This one. I hope that's the one you are looking for. Otherwise, just come to me after the presentation. I will give it to you. And like I said, if you just search for OpenJDK space CRaC, you will find it. It will pop up in Google. What can the methods in resource do? Can they store some metadata for restore in the snapshot? Well, you can think about that. Everything you store in variables, or maybe even files, you just have to make sure you restore them in the restore method. But everything is possible. So that's what I do, right? I take the current timestamp and save it in a variable, because then it will be checkpointed. The next time I restore it, I can just read the variable. So you can, whatever you like, you can do there. You can also create text files and then load these text files in restore. Or whatever files, it's possible, yes. It's just a method call that will be executed before the checkpoint will be created and after it will be restored. Or before it will be restored, sorry. Are there any other limitations other than I/O? Dynamic class loading? No, shouldn't be a problem, dynamic class loading. Because like I said, if you store the current state that includes everything that's loaded, when you restart it or restore it and then load something, yeah, it's fine. It's just a running JVM. With all the JIT stuff going on, that means if your application changes after the restoring, that means the behavior of users using your application, the JIT will optimize that from that moment on. It's really just think about pausing it, restarting it. Nothing happened there. We just store the whole thing and then restore it from memory. Is there a way to use it for AWS Lambdas? If yes, then how? There is in this GitHub repository, I think it's github.com/CRaC, you will find a demo for AWS Lambdas. And we added that last week. I didn't really take a look into it, but there is a demo and you can use it with Lambdas. Is CRaC already production ready? No, it's not. It's really under heavy development. So like I said, you can download the OpenJDK, you can play around with it. If you are really brave, you can use it in production, of course, but I don't want to really recommend that. But yes, it works, as you can see, I use it. So, but I don't know the side effects, sorry. Is there active effort to integrate this to JDK? Any plan? Yes, I would love to know, but I don't know. So we proposed that to Oracle as an OpenJDK project. They accepted it, so it is an OpenJDK project. That doesn't mean it will become really part of the JDK. I mean, hopefully it will happen. That's what we are aiming for. It depends on you. If you would like to see that, talk about it, ask them, just vote for it. I don't know. It's really awesome because you have to do something, okay, right? So you have to add this or implement the resource interface. But you saw the effect is awesome because it's so fast. It's unbelievable, and you don't need to create native images and stuff. Of course, GraalVM we are in the same range. I would say we are sometimes faster because GraalVM does different stuff. If you start a native executable, it's still something going on. It's not only loading back into memory, but we are just rely on the file system in principle. So we are definitely in the same range, and you gain the performance that you have from a JIT. The JIT is not a bad thing. It's great because that makes Java so fast. And you still have that. That's the good thing with CRaC. What problems, example with Hibernate sessions, we should expect? Oh, this is a good one. I don't know. Try it. Let me know. I really don't know what happens with Hibernate sessions. So I have no idea. Sorry. I don't know. It would be good to add graphs as comparison with GraalVM. Yeah, that really depends. I mean, we could do the same stuff with GraalVM. I agree. Maybe we should do that with the same demos. But you will see it will be in the same range. It's not really slower. But it's really depends on the applications that you do, right? We can't just use a really production application as a demo. So we usually do some stuff that we find somewhere that we can use for demos. And of course, we can then do a Graal VM build of that, but you will see that it is in the same range. Graal won't start in 1 millisecond, right? It will also be in the range of, let's say, 50 to 100 milliseconds startup time. But just to keep in mind, if you use Graal native image, you don't have the JIT. That means whatever then comes when your application is running, this is the stuff you get with AOT, but with the JIT compiler still there, you can really, it will optimize code, right? So this is that's the big advantage. It will be faster. JIT is always a bit faster than AOT. This is just a fact. Won't this acronym, okay, that's a good one. Won't this acronym bring unwanted attention from author? Yes. So yeah, CRaC is not the best name for it. Yeah, I mean, it's great. You can make jokes, bad jokes, but I mean, that's the shortcut at the moment. Maybe we will change it, but yeah, I don't know. Till now, nobody really complained about it. Does CRaC save a whole heap and metaspace? Yes, it does. So it really saves the complete stuff. So, and there are no more questions. We still have 3 minutes. So if there's someone from the audience still have questions, just let me know. Otherwise, I saved you 3 minutes. And thanks for attending.